Okay, so this is our second video. This one should be a little bit shorter than the last one. We are covering the measure of variation that goes with the mean. So that is the standard deviation. It's chapter 30.5. You really need to have printed the notes that go with the video. If you don't have printer capability, then of course you can have it up on a screen and then rewrite it on your homework, because that's the first notes. But more importantly, this is a worksheet that we're going to be doing together in the video. So you can either write on this or recreate this in your notebook. So last time we did the variation that goes with the median, the IQR. We also did box plots, which is a graph of all of that. Well, now we've got to come back to the measure of variation that goes with the mean. In real life, that's called the standard deviation. I apologize. I wanted to say one thing here. I'm saving you some work. When you go to do that exercise, that's going to be useful information. And I know on my original homework for number 8, I said just do the MAD. I do actually want you to do both of those. So this is a little bit of an updated homework past what is actually listed on the homework sheet. All right. I want to talk about standard deviation. That is the thing that's real life. That's what all powerful statistics uses. You do not have to draw this right now. We are talking about unimodal and symmetrical distributions, because that's what the mean is good for. Thus, that's what the standard deviation is good for, right? Well, obviously, you see some spread here. Here's the mean. I mean, just for example, again, you do not have to draw this. This would represent, I guess that data point is a little above the mean. That data point is way far above the mean. Here's a data point that's a medium amount below the mean. Here's a data point that's very far below the mean, etc. So it kind of would make intuitive sense that in order to describe the variation as a whole for this graph, for this picture, for this distribution, maybe if I could come up with the average variation, the average distance a data point is away from the mean. Now, how do we get averages? We add up things, we divide by how many, right? So you could take this one, because that's how far that data point is away. That's how far that data point is away, right? You could add all those up and divide by how many. There is one problem with that. Because of subtraction, these would be positive and these would be negative. But we could really look at it as a distance, or just make them all positive, add them up, divide by how many. But I know this is on your sheet, so you don't necessarily have to rewrite this if you've printed the notes. There is a difference between sample and population standard deviation. I just wanted to get these up here so I could point to things. About to write mu. And I forgot my sigma here. Sorry. I'm being lazy because I know you have the notes in front of you. I really want to look at this one first. X minus mu squared. Add them all up, divide by how many. These horizontal lines I was making up here, you could see that I was really doing this piece right here. Data point minus the mean. How far are you away from the mean? Okay. And I had said, well, if I could just make them all positive, add them up, divide by how many. You kind of see the add up, divide by how many. That makes sense, trying to calculate an average, right? For reasons we do not want to discuss in 207, theoretical statistics. It came up, well, I won't mention that, but We like to square things in statistics to keep them positive as opposed to taking the absolute value. So that's the only reason we square these, because these would have been positive, these would have been negative. When you put positives and negatives together, they go to 0. That does not have 0 spread. So we're going to square those distances. Add them up, divide by how many? Well, hopefully we all mathematically know that this square root does not cancel that square for actually lots of reasons. But probably the clearest is, well, the n doesn't have a square on it. And then we had the summation sign in the middle. But if you kind of come at it from a units standpoint, let's say this was inches or something. So if I square it, I'm up to square inches. Add them all up, divide by how many. I'm still at square inches. If I take the square root, I am back down to regular inches. Taking the square root at the end also helps counteract the idea that I just really blew up those distances, right? Because when you square something, it gets much bigger. It doesn't completely counteract it, but at least it brought it back down some. And then divide by how many. Now, when we were talking about the mean, we talked about how I'm referencing you. So we have this second formula. Now you will notice on whether I'm referencing you as a sample or as a population, that's lowercase sigma. These are different formulas. One divides by n, one divides by n minus 1. So it's not like the mean where they were the same answer. These are completely different numbers. Now you can already see how this is a little confusing. If and when you take Math 307, we will spend more time on this. But they wanted to be able to introduce some type of understanding of variation into particularly the Algebra 1 classroom. So about 8 to 10 years ago, the Department of Ed came up with something called the mean absolute deviation. Now again, a year ago, they actually removed this back out of the Algebra 1 classroom, but you never know when they're going to put it back in. So I'm still going to cover it. Your book still covers it. This is a totally made up thing. No one in real life ever uses the MAD. It's called the MAD for short. Real life is all about standard deviation, but you'll be able to see, particularly if you've looked at the formula, why it's much easier for kids in middle school to understand. This is the straight average. You do your subtractions, how far you are away from the mean. You take the absolute value, meaning you're making them distances. You're just making them all positive. And then you're adding them up, dividing by how many. So really, the mean absolute deviation, it is the straight average distance a data point is away from the mean. These, we still say it kind of in quotes. Oh, this is about how far a data point is away from the mean, but we know that's not precise. But it is the big idea of what are these formulas actually calculating? It's trying to calculate the spread. Because you can imagine, back to real life, if you had something much tighter, then your distances are much smaller. I'm going to be honest, in the Algebra 1 classroom, teachers usually will go through the work it out by hand the long way once with the class. Then they show the students how to do it on the graphing calculators. So when it comes to SOL time, it's very easy. The kids are just crunching it out on the calculator. When I teach 307, we actually learn how to do it on the graphing calculators. Here in Math 207, we're going to keep the data set small and easy just to give you the big idea, knowing that we will revisit these topics in Math 307. A few other things from the notes before we kind of practice this stuff. The mean is affected by outliers, so of course the standard deviations or the mean absolute deviation is affected by outliers. Students are real good at number crunching stuff, right? But we do actually want them to have some understanding as to what this measure of variation means. So I'm going to work on, this handout now. Okay, I'm going to recreate these 3 comparative dot plots up on the board. All I did was rewrite the formulas up at the top so we wouldn't forget what they were. Since you have it neatly in front of you, I'm probably going to do mine fairly quickly. I'm not even going to count. You have the good copy in front of you, right? Okay, these 3 graphs are supposed to represent 3 comparative dot plots. I did the best I could to line up the 5s about at the same spot, right? There's 4 and 6 ones over there. Obviously the 29 should be way out here, but I didn't want to take up too much room. So you can imagine the 29 actually should be like over here or something. So before you ever get into number crunching, getting the students, well, first of all, to actually calculate that the mean of all 3 of these is 5. That is not going to change. And that's the whole point of this activity, is just knowing the mean is 5 is a totally useless piece of information, like we talked about last time, if you don't know the measure of deviation or the picture to go along with it. This is the only distribution that a mean of 5 is valid for. Mean of 5 here means absolutely nothing. It describes none of the data points. I'm sorry, I did misspeak. This one is perfection, right? And this one is pretty darn good. He's unimodal and symmetrical. So in Math 307, I actually used 7 dot plots, but I wanted to make y'all's life easy, so I went with perfection, pretty darn good, and absolutely terrible of how the mean of 5 represents each one of these. There are 7 data points on each one also. All right, let's start this with what makes the most intuitive sense, even though it is actually not used in real life at all. We're going to calculate the MAD. So we're going to, how far is each data point away from the mean? I'm going to add all that up, divide by how many. Well, this is a data point of 5. How far is 5 away from 5? Well, 0. Now we have the second data point. He's the number 5. How far is 5 away from the mean of 5? 0. Since this one's perfect, we would actually have 7 zeros divided by 7, which of course equals 0. Right, I didn't need to do math to see that that has a spread of 0. I think I want to give me some lines separating. All right, let's do the MAD for each one. And I really like to do these calculations next to the pictures. It helps reinforce to the students, what the heck am I actually even calculating? All right, now remember the mean is 5 for all of these. So we actually have a data point of 1. How far is 1 away from 5? Particularly if you just let the students use the language of distance, which has to be positive, or you can make sure they're taking the absolute value of -4, whatever it takes to get to a +4. I have 6 of these data points. There's 1, 1, 1, 1, 1, 1. So I need 6 of these. And then how far is 29 away from 5? He's 24 away. 29 minus 5. That's all 7 data points, how far each data point is away from the mean. Remember, we're just doing that formula right there for the mat. Then I'm supposed to add it all up, divide by how many. And let's do the last one. So, well, first, perfection to terrible. You can see, yeah, spread of 0, spread of almost 7. Oh, bigger numbers mean we're spread out. Okay, this one. Okay, our mean is still 5. How far is 4 away from 5? But again, in a distance, an absolute value sense. That's 1 away. I have another data point of 4, so he's 1 away. Now I have 3 data points that are 5. Each of those 3 data points are 0 away. While mathematically, I do not need to show those plus zeros, I'm going to show you why in a minute that I make sure to do that. And then the 6s, I have 2 of them, they are 1 away. And I'm supposed to be dividing by 7. I have so many students that if they don't show those zeros, they end up dividing by 4. You have to remember for all of these, the n is 7. So I like to have zeros as just my placeholder so I don't forget that I did actually average 7 data points. That turns out to be 0.57. So yeah, because he was pretty darn good. This one was terrible. You know, almost 7 versus a half. So I think it's really important, even if you just do the mean absolute deviation, that you actually have the numbers next to the pictures in some type of comparative, in this example, comparative dot plot way, so the students can make some sense as to, oh, sure, I know how to calculate the numbers you gave me, but what does it mean? It is describing the spread, how far out the data is spread. So that's the easy level, and that's why it was introduced 7th and 8th grade, but it's actually not real life. So we are going to keep going to calculate the standard deviation. It's just a tiny bit harder. You just got to stay organized. Now, if you look at the top of your sheet, the standard deviation formulas, the numerators are exactly the same. It's basically how far from the mean you are, but we're going to square it. So it's really all these numbers we already did in the numerator for the mean absolute deviation. That's how far away we were, just in positive, right? Well, now we just got to square it. So it might be, let's call this the numerator of, I don't care if you're talking about S or sigma. I just need to square all those. It's a bit overkill, right? I'm squaring 0. So I just get 0. Now, for the sample standard deviation, I have to take the square root of 0 over 7 minus 1. For the population standard deviation, I have to do 0 over 7. Again, this is total overkill since everything is 0, but I wanted to make sure that you're catching the standard deviations have different formulas. In the bottom, this is n minus 1 and that is n. It will get more interesting when we get to the second one. All right, let's do that numerator again. I just have to square each of those. 4 squared plus 4 squared plus 4 squared plus 24 squared. That gives you 672. That's just the numerator of the formula. So now S is the square root of 672 divided by 7 minus 1. Sigma is the square root of 672 divided by 7. Just make sure you don't forget to take the square root. That will give you 10.58. That will give you 9.8. I want to finish getting these numbers, but then I want to show you so many other little connections that you can make from this example. I'm going to have to write pretty small here at the bottom. So, the numerator, 1 squared plus 1 squared. I'm not going to write those zeros. Plus 1 squared plus 1 squared. That would give you 4 for the numerator. So S is the square root of 4 divided by 6. Sigma is the square root of 4 divided by 7. Okay, good. I was able to fit it on the screen. So again, you could compare just the MAD and getting the students to understand that yes, this one should have the biggest number. That one should have the smallest number. You could do that with just the population standard deviations if you wanted. Yeah, that's the smallest. That's the biggest. That's just a little bit bigger than perfection, right? 0.76. If you wanted to get some number sense in here, this denominator is smaller than that denominator, right? So what does that mean in fraction form? When you divide by a bigger number, your entire fraction is smaller. Let me say that again. This denominator is bigger than this denominator. Since it's a denominator, a fraction, this number is smaller. And of course, you'll see it here. This number is smaller than that. That number is smaller than that. Of course, we don't see it with the zeros because zeros are special. I presented it to you in what I call a horizontal way. Many Algebra 1 teachers actually present it in the vertical way. They'll have columns coming straight down. So what I did was prep a shorter vertical way. This is example number 2, the ones in the 29 dot plot. This was part of the notes I loaded. I just wanted to show you, for example, how some Algebra 1 teachers will do it. They'll write the data set, then they'll have columns up here, like for example, hey students, take the data point minus the mean, and then do the absolute value. Then you add it up, the sum, and then to find the mean absolute deviation, the sum divided by how many data points. So that matches our 6.86, right? And then to help them get the standard deviations, since they already have this column, they'll have them square each one, add it up, and then you have to take the square root of that number divided by either n minus 1 or n. So this is exactly what I just did on example number 2. This is just showing things horizontally. This is showing things vertically. It's all the same thing. I just wanted to present it slightly different because I do find that some students of all ages have a preference on whether they look at the work going horizontal or whether they look at the work vertically in columns. So that's what this is about, just a different way of presenting the exact same material, but I, again, only did it for dot plot number 2. You will absolutely, for a very small data set, be responsible for calculating mean absolute deviation and also possibly the standard deviations on a test. I know some of you have the graphing calculators. Some of you may already know how to get these off the graphing calculator or how to program your graphing calculator to actually calculate the MAD. Even if you have a graphing calculator though, I'm not going to just accept the answers. You have to in some way, like the work we just did here, show me that you know how to calculate it out by hand. Now, of course, you're going to need a calculator to take a square root, but I'm saying you can't use the shortcuts on the graphing calculator for this topic from my Math 207 course. All right, let me see if I forgot to tell you anything. Now, I put your homework up at the beginning, so just recalculate this, do a couple of the homework problems. Our next video is still going to be dealing with standard deviation, not really number crunching like this. It's called the empirical rule. They are word problems. It's probably the next spot that if students are going to struggle in my stats portion, the next video is the material that sometimes they do and they need more practice with. So this stuff's pretty easy. Just make sure you practice it.